Hey, this is Mr. Leach from Simpson Math, and this is our fifth video on exploring algebra tiles. Today, we are going to be talking about factoring quadratic trinomials. If you have yet to see any of your previous videos about exploring algebra tiles, you might want to look back at a few of them, specifically the previous one, the fourth one, about multiplying binomials. Our first example is x squared plus 7x plus 12. If you watched the multiplying binomials video, this trinomial should feel pretty familiar. It was the answer to one of our questions. In this video, we are going to see how we can go backwards from x squared plus 7x plus 12 to the two binomials that when you multiply together, you get this trinomial. That's called factoring. If I asked you to factor the number 8, there's a few things we can multiply together to get 8. 1 and 8, or 2 and 4. Those pairs are the factors of 8. Here we have a trinomial. We need to see what we can multiply together to get this. That's called factoring. There is a special type of factoring when it comes to factoring trinomials, and that is the focus of this video today. So we have x squared plus 7x plus 12. If you think about the answers from the previous video, they were rectangles. The x squared, the x's, and the constants work together to form a rectangle. And that's what we need to do today. Two quick things to point out again. This x squared is literally x times x because the length of this x is the same as the length of the x squared. So this literally is x times x. But there is no amount of constants that I could multiply together to get x. It doesn't make sense to have 5 added together and get an x. That just doesn't work. So it's notable that those lengths aren't the same, and that's by design. But it is important that the width of this x is the constant that'll play together when we start factoring this. So I could put all the x's like this, but the problem is that's not going to make a very good rectangle because what do I do with these constants? Well, I said a second ago I could put the constants here on the ends of these x's, but I'm going to run out of x's or run out of constants, and this isn't going to make a rectangle because I can't stack x's up over here for this to equal. Remember, I just said no amount of these constants will equal an x. This might be tempting, but it doesn't quite equal. It's a little short. So I need something to go over here. Well, remember this is x times x, so somehow I have to get that x times x to get x squared, and that's it right here. This would work if I had a different question. If I had x squared plus 7x plus 6. I don't have x squared plus 7x plus 6. I have x squared plus 7x plus 12, so we have to somehow use these constants. Well, I can move this one over here. This one doesn't have a home anymore, so it needs to swoop over. Let's see if this works. Better, but I have 2 left over again. Well, let's try to do that same thing. Let's move this one over here. That fits. These don't have a home anymore, so they can slide over here, find their home right here. And now I have a rectangle. What's important about this rectangle are the lengths here. This length is x. Each of these lengths is 1. So if I put them together, I get a plus 4. So this length together is x plus 4. So that means that this is x plus 3. So that means that if I was to multiply this together, if I was to multiply x plus 4 times x plus 3, we would get this. So that means that this factors into x plus 3 times x plus 4. It does not matter which one you write first because multiplication is commutative. You might be thinking to yourself, didn't we just do this problem? And you'd almost be right. Instead of a 7x, this is an 8x. Again, we saw this answer in the previous video, but now we're going to be working backwards. take just a second and try to see what you can do with this on your own. Okay, just to check here, remember, this doesn't work. I need to have at least an x on each side here, so that way we get the x squared, and so that way the constants have something to go. So try to fill in the constants. If that doesn't work, adjust your x's to see what does. Okay, so I've attempted to put everything together, but this isn't quite a rectangle. We have some empty space here and here, so we need to attempt to fix this. I can't get rid of this one, but I can move this one. If I do that, this piece is a straggler out on its own, but it does have a nice home right here. So there we have it. Now we have a nice, neat rectangle. So now all we need to do is to count up the sides. This length is literally x. Each of these are a constant, so this is going to be x plus 6. This is literally x, and each of these lengths are constant, so this is x plus 2. So if I'm to write this down, I have x plus 6 times x plus 2. If you think you're seeing double, no need to get your eyes checked, because this is a negative 8x. So these positive 8x's need to turn into negative 8x. The same rules are going to apply as before. Just fit the algebra tiles together as a rectangle. This is the same arrangement as we saw a second ago. We have an x, and then 6 constants, and then an x, and then 2. But this time, the 6 and the 2 are negative. So we have our same x as before, but this time we have negative 6, or minus 6. And then we have our same x, but this time minus 2. So we end up with x minus 6 and x minus 2. So our final answer is x minus 6 times x minus 2. This one again is pretty similar. We have our friendly 12, but this time that 12 is negative. So this is going to throw things off just a little bit. Let's do this one together. I have x squared, x, and then my negative 12. This x I know I can put together with this x squared, but what do I do with all these constants? I can't just start sticking them together because I know this is not forming a rectangle. So I need to do something different. One thing that I can do anytime, ever in math, when it's useful, is I can add 0. What we're about to do is to add a 0 pair of x's. This is a positive x, this is a negative x. So when I add them together, I get 0. So I'm going to be adding them in. So if I add in 0, does that change the problem? No, because if I just add 0, it doesn't do anything. A lot of students confuse 0 and 1 sometimes. 1 is the identity value with multiplication. So if I wanted to not change anything and I'm multiplying, I can multiply in a 1. But here I'm adding, and the identity value for adding is 0, so I can add in a 0 whenever I want to. If I wanted to, I could add in a 0 pair of constants, but that's not going to help me here. If I wanted to, I could add in a 0 pair of x squareds, but that's not going to help me here. It is going to be helpful to add in this 0 pair of x's. So let's do that. I can put these together, but I need something here as well. How about the positive x's join with the positives, and this negative x goes to the other side by itself? Well, now I can fit in these negative 2 here. That's good. Well, let's add in another 0 pair of x's. I can add in another 0 pair of x's. This time I have a plus 3, x plus 3, and an x minus 2. I can fit in a few more. I like this. Let's keep going. I can add in a third pair of 0 pair x's. This will give me x plus 4 across the top and x minus 3 across the bottom. I can fill in with the rest of these constants, these negative constants. So here we end up with x plus 4 and then x minus 3. So our final answer is x plus 4 times x minus 3. I'm going to want you to try this next one on your own. It's similar with our negative 12, but this time it's a negative 4x in the middle. So pause and try this on your own. I'm ready to add in my first pair of 0x. So I'm going to add the negative x with the other negatives and the positive x here. I can start a row. Clearly I'm going to need to keep going. So we end up with x minus 6 and x plus 2. So our final answer is x minus 6 times x plus 2. Again, you can write that in any order you want to. Now that we've seen one of every type, let's look at ones that have an a of 3. When I say a, I'm talking about the standard form of ax squared plus bx plus c. So the a is 3. Doesn't really change things too much. Just going to have more algebra tiles to work with. When you're factoring, it's probably a good idea to start with your x squareds. Think about all the different arrangements you could do with your x squareds. Well, I can only arrange these x squareds in terms of a rectangle in two ways. I can arrange it by 1 by 3 or 3 by 1. Since it's a little tight on space for me, I'm going to work it this way. So let's put our x's in place. We can have 1 right here, and these 3 belong down here on bottom. So now I actually can have my 3x squareds because I'm multiplying 3x times x. And then one of our x's has a home. So let's continue with our process of putting in our other x's. Well, let's look at our constants. I'm in a bit of a bind here. I only have one constant remaining, and I already see that this is not going to work out. So let's take a look at the constants. This is something you could do from step 1, but it's helpful to look at. How many different ways can I arrange these 5 constants into a rectangle? Really just one, technically 2. So here's I can arrange into 5 by 1 or 1 by 5. So I can't use this x here. So that means I have to have either a single row or a single column. I know that the single row won't work out because I have so many x's. So what I can do is I can take my constants and go and place them in this single column because it's the only option I have. Get rid of this one. So that means the rest of these x's should fit in right here. Let's find out. Yep, looks like it worked. Across the top, I'm going to have 3x plus 1. And across the side, I have x plus 5. Replacing the algebra tiles with numbers, we get 3x plus 1 and x plus 5. So that means my final answer is going to be 3x plus 1 times x plus 5. I'm going to want you to try this on your own. We have 4x squared minus 16x plus 15. One thing to keep in mind is think of how many different ways you could arrange the 4x squared into a rectangle. Think how many different ways you could arrange 15 into a rectangle, because that's going to come into play as to how many different possible combinations you can come up with while you're building your algebra tiles. So take a second and see what you can get while playing around. So I decided to try the x squareds in arrangement of 2 by 2. I'm on my last set of tiles to place, and I noticed something. I only have 6 constants remaining, so I know I don't need to wrap another set of x's around. So I'm just going to put a set here and a set here. So here I end up with 2x minus 5 and 2x minus 3. Let's multiply those together. 2x minus 5 times 2x minus 3. So here's the next one. Let's try 4x squared minus 5x minus 6. Use the concepts from the previous examples to try to do this one on your own. So I have my 4x squares arranged in a row like this. Let's put our x's in place, our negative x's in place. It is tempting to do this, but this is a bad idea. The reason why that's a bad idea is because what is a negative times a negative? A positive. That should be a positive if this is a negative times a negative, but this is a negative 6. So I got to keep all my negatives on the same side, whether it's here on the bottom or over here on the right. Try and see what you can do from here. So what I did is I added in 3 0 pairs of x's. When I did that, everything fit into a rectangle for my x's and my x squareds, and then I noticed I have 6 negative constants. So they just fit in right here. So there's my happy pretty rectangle. So I have 4x, and then plus 3, and then x minus 2. So my final answer is 4x plus 3 times x minus 2. 2 more problems, and there are the special case questions. So I have 4x squared minus 25. Obviously no x's here, and my c, yes, that is still the c, even though there's only 2 terms, it's that last term and it's the constant. That c is negative, so that means I'm going to have to add in some 0 pairs. Try this on your own. So far, I've added in 1 set of 0 pairs of x's. I'm obviously going to need a lot more. I'm leaving my x squareds in this square pattern, this 2 by 2, because every time I add in a 0 pair of x's, it's going to keep my b's at 0. If I had it in another pattern, when I'm adding in my 0 pairs, I'm going to end up with either more positives or more negatives of x's. So that's just not going to work for this particular question. So let's keep it in this form. So here we have our final arrangement of the algebra tiles. We have 2x plus 5, and then 2x minus 5. Put that together, and we get 2x plus 5 times 2x minus 5. An important note to make about this binomial is that it is the difference of 2 squares. This 4x squared is a perfect square. If I square root it, I get 2x. This 25 is a perfect square. If I square root it, I get 5. You might have seen it written like this. A squared minus b squared is a plus b times a minus b. And we can see that evidence in this set of algebra tiles. 2x plus 5 times 2x minus 5. This entire set of 10x and this entire set of negative 10x will cancel out to 0. If you're watching this video actually using and playing with algebra tiles, you notice something going from the last question to this question. Setting up this question uses the exact same number of algebra tiles in the exact same configuration as our previous answer, except all of our 0 pairs that we added, flip them over so that way they're all positive, our positive 20x, and then our negative 25 became positive 25. So that should tell you something about the arrangements here. So start setting them up and see what you can do. Let's check what we have so far. The x squared's in this pattern, and this is working out so far. This would be 2x plus 2, but I have a whole lot more to work with, so let's just keep adding them on and see if we can get our square or rectangle. So let's check our work. We end up with 2x plus 5 and 2x plus 5. So because I have 2x plus 5 times 2x plus 5, what happens if you multiply something by itself? You can just write it as a square. So this is going to be 2x plus 5 squared. This particular trinomial we call a perfect square trinomial. The reason for that is because once I factor it, it literally is a perfect square. 2x plus 5 squared is this. And you can also see the shape that it makes. It is still technically a rectangle, but even more specifically, it is a square.